Hey everyone, so today we're going to learn a little bit about acceleration and the kinematic equations. So the goal here is to understand and apply mathematical formulas to describe an object of motion. So this is important because actually it's really cool that we have precise equations that explain or basically describe motion. That's what the kinematic equations are. They describe motion with constant acceleration. So it's really neat that we have these equations so we can make predictions of certain values. So when it comes to acceleration, so we've dealt with velocity and we dealt with uniform motion. So velocity was constant. Acceleration happens when velocity is not constant. So when velocity is changing, whether that be velocity is increasing or decreasing. In both cases, we have acceleration. Technically speaking, acceleration is the change in velocity over change in time. That's what the definition of average acceleration. I kind of wrote here the acceleration in terms of components, the horizontal and vertical components, because that'll be useful later on down the line. So if we're dealing with two-dimensional motion, the horizontal stuff is a subscript of x, and the vertical stuff is with the subscripts of y. And in terms of unit analysis and thinking about acceleration, when we have change in velocity over time, velocity has units of meters per second, time has units of seconds, at least these are our SI units, so that leaves us with meters per second divided by seconds, which when we simplify becomes meters per second squared. Right? But this kind of unit analysis helps us kind of realize what acceleration is. It's the amount of velocity that changes per unit time. Right? So even though we simplified as meters per second squared, I kind of like this meters per second notation of writing down acceleration just because it kind of makes a little bit more sense in terms of what acceleration means. And I also want to note that acceleration is a vector quantity, so not only do you have to state the value of the acceleration, but also the direction. So kind of a quick computation here. So let's suppose we have a 1997 Porsche, and it goes from 0 to 60 miles per hour in 3.6 seconds. Let's also suppose we have a 73 Volkswagen Beetle, and it goes from 0 to 60 miles per hour in 24 seconds. How do their accelerations compare? So let's compute the acceleration for both. I'm going to kind of skip over drawing a diagram, but if we write down the change in velocity for each car, for the Porsche, our change in velocity is 60 miles per hour, and it has a change in time of 3.6 seconds. Right? So if we calculate the acceleration, we have 60 miles per hour per 3.6 seconds, which when we simplify that becomes 16.7 miles per hour per second. Kind of a weird unit, but it doesn't matter because we're going to compare it to something with the same unit. So for the Beetle, I did a similar calculation, except for this time it goes from 0 to 60 in 24 seconds. So the acceleration is 2.5 miles per hour per second. So we can see here that the Porsche accelerates at a much more rapid rate. For every 1 second, it increases its miles per hour by 16.7, whereas the Beetle only increases 2.5 miles per hour every second. So kind of visually, you can kind of see the difference there. Now here is a ridiculously important and useful slide. Basically, we're going to have different situations here. We're going to have situations where we have a positive velocity, a negative velocity, positive acceleration, negative acceleration. So kind of how to describe the motion of whatever object we're looking at based on whether its velocity and accelerations are positive and negative. So the four situations. So let's look at here probably the one that makes the most sense: positive velocity and positive acceleration. Right? So positive velocity means that we have some amount of positive displacement over time. So in thinking about, let's assume we're looking at a person. Let's think of a car. I think a car would be a good example. So we have a car that has a positive velocity. That means our car is moving in the positive direction. Right? That's literally what it means. So we're moving in the positive direction with a positive acceleration. So that's like if we hit the gas. So our acceleration is positive, meaning we have an increase in velocity over time. Right? So that means our object, our car here, is moving in the positive direction and speeding up in that direction. right? So both these vectors are pointing in the same direction, they're both positive. Now, let's look at the situation in the bottom right corner where we have a negative acceleration and negative velocity. Note here that both these vectors are in our negative direction, so they still point in the same direction, just both negative. So having a negative velocity means we have a negative displacement, and a negative acceleration means our speed is not getting slower and slower, but it's getting more and more negative. So our speed's actually increasing. So in this situation, our car is moving backwards, and we're like speeding up as we're going backwards. Now the other two situations are when our velocity and acceleration are in opposite directions, or vectors point in opposite directions. So let's say we have a positive velocity, negative acceleration. So let's say we're moving forward, but we're decreasing in velocity over time. Right? So that basically, that's as if we hit the brakes. So this is an example of, I don't like this term, but this is deceleration. Right? I always like to think of acceleration as positive and negative. I'm not a big fan of the term deceleration, just because it can be kind of ambiguous and lead to misconceptions. That's what's going on when velocity and acceleration have opposite directions. So kind of conversely, we can have a negative velocity and have a positive acceleration. So what's going on there is negative velocity means we're moving backwards, right? That's what the negative there means. And having a positive acceleration means our change of velocity is a positive change over time. So that means we're slowing down. Right? So again, here you can think of that as deceleration. Right? So yeah, that's basically it. So I always like to think about the vectors. If the vectors are pointing in the same direction, the velocity acceleration vectors, then we have the object speeding up. If they're pointing in opposite directions, it's slowing down. We're going to be using that idea throughout this course, so start getting used to it. And finally, here we have the kinematic equations. These will become your best friends. I'll say this right out front, the kinematic equations can only be used when an object has constant acceleration, right? So kind of in reference to something we haven't even learned yet, but forces. This means that we have a constant net force acting on the object. But nonetheless, so we basically have three different equations here that can be used to describe the motion of an object. Right, so the first equation here, I'm going to call the velocity equation. So this states that the final velocity of our object is equal to the initial velocity of our object plus its acceleration times the amount of time it takes to go from that initial and final location. We also have a position equation. So this says our final position is our initial position plus our initial velocity times time plus 1/2 the acceleration multiplied by time squared. And then we have the time-independent equation. This basically just take the velocity equation, substitute into the position equation, rearrange and solve. I call it the time-independent equation because this is the equation that does not have time. And this says that the final velocity squared is equal to our initial velocity squared plus 2 times our acceleration multiplied by our displacement. So these three equations are going to become very useful to you. You're going to use these all the time. I know the subscripts can be a little bit daunting right now, but you'll get the hang of them. And we're going to be using these in a number of examples. So I also want to note here with the subscripts, X is used throughout, right? This does not mean that we're only limited to the analysis just horizontally, since most of the time X is used to describe a horizontal axis. We can also deal with say, a y coordinate system. So just anywhere that we have X here, we replace with Y, and the equations still hold. If we decide to use a z-axis, we can replace x with z. It doesn't matter. But we're just going to use x here just because that's what the formula sheet has, so we're going to work with it. So I'm going to skip this example and do it in another video. But I do want to mention a little bit about parabolic or quadratic motion. So if we had a situation in which, so let me go back for a moment, this position equation, if our initial position is 0 and our initial velocity is 0, then our equation then simplifies to say that x is equal to 1/2 at squared. So I have written that here. X is equal to 1/2, so 0.5, with acceleration multiplied by time squared. So x is proportional to t squared, which is a quadratic relationship. Right? So you're probably used to thinking, well, quadratic, that's y is proportional to x squared, right? But here we have x proportional to t squared. Right? So just don't confuse those x's. Those are two different x's going on, so to speak. Here my y-axis is x, and my x-axis is time. Right? So then that's what this graph here is showing. We have a quadratic relationship. So we can kind of use this to help us answer problems. Sometimes we don't have to use the full kinematic equation to solve anything. We can just use quadratic analysis. I'm going to go into that with detail in the next video. So the last thing I want to mention are some tactics when solving one-dimensional motion problems. So basically, when you approach a word problem, these are certain things you want to do. So first, draw a diagram. Right? Show the objects at its beginning of the motion, at the end, and any other point that's going to be useful in the analysis. So if there's some sort of characteristic in which the motion changes, that would be useful. Don't make very elaborate drawings. These are just to help you figure out what's going on. So a lot of times when we're dealing with drawings, if I'm trying to draw a car, I literally just draw a box. It's far simpler and gets the job done. So the second thing we want to do is establish a coordinate system, so state which way we're going to call a positive direction, and whether we're using x-axis, y-axis, whatever axis we're dealing with. So basically, state which way we're calling positive. And the next thing, we're going to define symbols, so state what we know and what we don't know. Most of the time, it's going to be the variables used in the kinematic equations. We're going to label the positions if we know certain positions. We're going to label velocities if we know velocities, accelerations, and time. And let's see, so step four is to solve the problem. Okay, seems simple enough, but I do have a kind of a systematic approach when solving problems, because we're going to use variables until the very end. If you plug in numbers ahead of time, you're not going to be a happy camper in this class. The AP exam very rarely uses computational or uses numbers in their problems, their free response problems, so written response problems. So I'm not going to allow it either. So you need to use variables until the very end. So basically, the only number I'm going to let you plug in the beginning is 0. So you write down your equation, plug in the zeros, rearrange for what you're solving for, plug in numbers, and get an answer, and then check if your units make sense. So that's kind of what the reflect here, step 5, has to do with. You're going to check to see if your answer makes sense. One could be that just the numerical value seems reasonable, right? So if I was calculating the speed when I'm running, and if I got an answer of 500 meters per second, I can't run 500 meters in a second. That seems unreasonable, so I probably made an error somewhere. And another easy way to check reasonability is by checking the units, making sure your units ended up being correct when you plugged in numbers. Alright, so that's actually the last thing I want to talk about in this video. The next video is going to be solving a whole bunch of examples, so you can kind of see how to systematically approach solving problems, how to think about problems using the kinematic equations, as well as solving problems just kind of through the analysis and thinking about what the physical quantity actually means.